Okay, thanks for joining. My name's Chris Gonning. I'm from Pentair Environmental Systems. I'm going to show you an example of the instrument set, the sensor package that we would deploy at a port by looking at an actual port installation. So the photo you can see in front of you is an actual port in British Columbia in Canada. It's called Nanaimo Port at Duke Point. It's a container loading port. It's got fairly good facilities. It's on Vancouver Island, so it's a little bit to the west of Vancouver itself. And yeah, this is a location that we've installed a fairly comprehensive monitoring system that takes a wide range of environmental parameters, pretty much all the parameters that can be measured and broadcast on the automatic identification system network called the AIS, which is a radio system that every major ship or either cargo or passenger carrying vessel in the world is mandated by the IMO to have. So what we do is we provide the instruments that measure the parameters that will help make the journey of that ship as safe and as efficient as possible. So this is the port, a particular port. We have located our system at this port on the Dolphin at the end here. This is a fairly typical installation. The advantages of the Dolphin are that it gets you away from the main entry and access into the port. Obviously, any ships coming in, there's a lot of ropes and anchors and vehicles and everything around on the main part of the loading terminal. So we've put our instrumentation over on the Dolphin. An advantage of the Dolphin is with other ports that might be in a hazardous zone, that is often outside the hazardous zone, or else given that a lot of these parameters are, while localized, they're also, could be measured further along the breakwater if we had to. So in this instance, the Dolphin here gave us the best compromise between a nice, sturdy, stable location and somewhere that was going to be representative of any measurements that we would make that would affect ships coming in and out of port. So obviously, if you're going to measure tide, current, waves, wind speed, things like that, you need to be relatively close to the spot that you want to measure. So to have a look a bit more detail, this is the Dolphin from land level. So this is the access walkway. Here's the station itself, so you can see it's quite a compact station. This is what we can see is the above water instrumentation. There's an instrument in the water that is designed to measure surface temperatures, salinity. Salinity can tell us, I guess, when freezing is most likely to occur. And underwater is an instrument to do triple duty monitoring of tides, currents and waves. So that's very comprehensive monitoring. And not only is it currents and waves, but it's current profiling. So it's installed in about 20 meters depth of water, depending on the tide cycle, and it will give us current measurements throughout that profile. Now, I'll show more information on that shortly. So the station itself, quite compact, quite modular, easy to install. Once it's locked down, it's very secure. We try and make the system to be as low maintenance as possible. So wherever we can, we use non-contact instrumentation. Wherever we can, we use solid state equipment. So trying to eliminate oil, moving parts, anything mechanical, anything that might foul over time, anything that might get biological growth such as barnacles and things like that on it. So that's a general principle of everything we do, that we try and make sure that it is as maintenance free as possible. To give you an idea of scale, that's one of our guys responsible for the installation. So you can see it's about a 3 meter high mast that most of the equipment is mounted on. To show you the instrumentation up the top, so this is a fairly comprehensive station. The instrument that does most parameters is this piece of gear here. So at the top is a 24 gigahertz radar rainfall. Now the reason we go for radar rainfall over a tipping bucket typically is that it is no moving parts. So it will give us rainfall size and intensity, from which we can calculate totals. It's a, as I said, no moving parts. The advantage of that is that the same model can be used for land installations as we can use for buoys or other floating platforms where a tipping bucket cannot be used. So underneath the radar rainfall, we have a two-dimensional ultrasonic wind speed and direction. So that's a wind speed and direction with 4 heads, so 2 pairs. The range of the instrument is 0 to 75 meters per second. It will give an accuracy, a typical accuracy of 0.3 meters per second over the bulk of that measurement range. The wind direction is accurate to 3 degrees, and unlike mechanical sensors where they have a dead zone because the instrument has to mechanically turn full 360 degrees, this instrument has no dead zone. So a lot of instruments will give a false reading around north. This is a true reading around north. There's 2 models of this wind speed and direction sensor. As I said, the figures are 0.3 meters per second accuracy and a 3 degree accuracy on the direction. There is a model, the next model up, which does do 0.2 meters per second and 2 degree accuracy if you really require it, but given that this is a practical operational port, those are within the accuracies required. Inside the instrument, we've got barometric pressure, so we can look at barometric pressure and tendency, which if we look at tendency, if we see pressure rising or falling, we'll have a leading indicator of whether a storm is approaching. And there's also a directional compass in there. Now the advantage of the compass is that particularly for taller elevations, when you install the wind direction sensor, you don't have to worry about aligning the wind direction sensor to true north. With the compass, we can take the installed reading of the wind direction sensor and use that as a basis for all wind direction measurements. So that's particularly useful where we might install on larger locations like the top of a gantry or a loading crane or anything like that, where it's often hazardous to do extended work in those locations. And then finally, we've got in the radiation, the naturally aspirated radiation shield. So a wind-cooled radiation shield is air temperature and relative humidity. So the temperature sensor is accurate to 0.2 degrees C, and the relative humidity is accurate to plus or minus 2% RH over the full humidity range. So it's quite a compact sensor, quite a high performance sensor. From those measured parameters, we also calculate the derived parameters of the Beaufort scale, which is a 0 to 12 indicator to show the severity of the winds. We will look at wind gust peaks and the direction from where the peak winds are coming from, so that obviously the taller ships, as they come into port, wind gust will have a big bearing on the movement of the ship in port. As it does its kind of final approach, and we've also got wind chill information for the comfort of the people working in the port, and we also calculate dew point to tell us when condensation is likely to occur. So there's a lot of derived parameters along with the measured parameters, and all of those parameters are part of the standard that can be broadcast over the AIS network. So the other very obvious parameter is this instrument here, which is a infrared forward scatter visibility sensor. It will typically give us measurements in the range of 10 to 32 kilometers. That's the general operating range. It will give us plus or minus 10% accuracy over most of that distance range. So visibility, if we're coming into port and it's high fog, high mist, or anything like that, then visibility will tell the ship captains prior to coming into port, maybe they need some assistance coming in, maybe they need, maybe it's unsafe to come in and maybe they should stay where they are. So visibility is a very important parameter. We can get measurements less than visibility of 10 kilometres. It's simply a matter of the accuracy of those measurements. So yeah, plus or minus 10% of the measurement in the range of 10 to 32 kilometres. So that visibility sensor is often associated with airport type measurements. Along with that are the communication systems that we've got on board. So the number one system is this antenna here, which is an AIS, Automatic Identification System radio antenna, which is 160 megahertz in the 160 megahertz band. That is the communication system mandated by the International Maritime Organization, IMO, that all ships carrying passengers and all ships above a fairly low cargo threshold must use the AIS system. Now, I won't go into too much of the rest of the details. AIS is obviously a well-known standard in the industry. We use a subset of that AIS called aids to navigation, and the system will take all the measured information and it will broadcast it over the aids to navigation subset, which uses message 21 and message 8 for those who are interested, and broadcast the environmental information to anyone within the region, anyone who can hear it either directly or through relay stations or through one of the web interfaces, what the current conditions are. So that's a very powerful tool. It's a free communication method, internationally mandated, used by every vessel above a certain size that needs this information. Alongside that, we've got this antenna here, which is a GPS antenna. So obviously for a shore-based system, it's only at the time of setup, but we often put these systems on buoys, so GPS location is particularly relevant there. And then over here we have a 3G cellular antenna, because the data that we get is not only broadcast on AIS, but it is distributed over a much wider area to our web platform that I'll show you later, where people can view the information from anywhere in the world. So another advantage of this system is if you put these locations in an area that's not well covered by AIS, the station can function as an AIS receiving station. So this antenna here will listen for ship position reports that will be updated depending on the speed of the vessel. If it's at anchor, it's around every 10 minutes. If it's moving fast, it can be every few seconds. So that ship position report, which says the ship identification, the current position, the bearing, the speed, and all that relevant information, the AIS network can receive that, and we can then use the cellular network to rebroadcast that to a VTS or a VTMS system that's outside of AIS communications to each location. So you can use these stations to extend the coverage area of your AIS reception area. So from a certain location, you might get 40, 50, maybe 60 nautical miles in ideal conditions. With this AIS receiving station, you can effectively create a receiving station anywhere you want, provided that you have cell coverage. Obviously, we've got other versions which can do satellite communications if you're outside cell coverage. So they're the instruments up the top. There's not a single moving part among them, all fairly low maintenance. The optics on the visibility sensor are relatively self-cleaning, although occasionally it will need a small wipe. Here's the station itself. You can see everything up the top that we've covered. The cabinet itself is on a powder-coated aluminium, marine-grade aluminium stand, stainless steel cabinetry. This instrument here is an oil slip detection system. So being a loading terminal and being in an environmentally sensitive area, the oil sensor is used to detect anything more than a 5 micron sheen. So anything more than the thinnest of oil layers, that instrument will scan the surface. It has a light source which will cause the hydrocarbons to fluoresce, and the fluorescence of those hydrocarbons will result in us saying we have an oil spill. So that instrument is a spill or no spill detection, and it will also detect ice. So it's quite a flexible platform. And then we also have, just hanging over the side here, an instrument that goes into the water that will look at salinity and water temperature, both of which tell us when ice is likely to form. This is an area where that does happen from time to time, so the instrument set will help detect and tell us when that is occurring. Finally, underwater in a depth of around 18 to 19 meters is an acoustic Doppler current profiler. So this ADCP gives us the complete set of information. It gives us tide, it gives us from which we calculate tendency, it gives us current profiling. So throughout the profile from the instrument to the surface, every 1 meter we will get current, speed and direction, and it gives us both wave height, which is the peak of the wave in terms of wave and surge, and it will give us the direction of the way that the wave is traveling. So, and of course period between the waves. So any ship coming in terms of the hydrographic parameters that's going to affect it navigating into port, it will know well in advance of what the tide, current and waves are to help either use more pilot's assistance, more tugs, fewer tugs, whatever they may want. And this is the control center where all the operational decisions are made. So there's multiple operator desks. Each operator can independently control their consoles, and management people or viewers within the control center can see the main displays, which are updated in real time. So this is a traditional map-based display where all ships who are broadcasting AIS information will have their position displayed on the map. We've got some dials down here showing us all the environmental parameters that I'll go into more detail later, and we've got CCTV tracking. So the sensor set here is AIS position reports supplemented with radar identification, and if a ship is identified either through AIS or radar, it can be automatically tracked with PTZ cameras fitted in strategic locations to monitor suspicious behaviour or maybe to assist navigation remotely. This is a traditional map view. This is a more modern kind of 3D representation of everything, including things like laneways. So specific laneways are defined that ships are supposed to be travelling in. The system can do geofencing that if a ship gets outside those laneways, it will flag an alarm and the camera can automatically track it. Being in such environmentally sensitive areas, any ship that wanders off course can potentially cause a lot of damage or can become a hazard by either going into areas where recreational craft are supposed to be, or potentially coming around a corner and causing a collision hazard. And down the bottom here, these are similar terminals, with this being the set of dials used to display the information that is being collected on site. And this is a close-up of the information from site, water level and trend. So you can see the current level numerically and on the dial, and you can see the trend on whether it's rising, falling, or what the trend itself is doing. Water temperature numerically on a dial, salinity, precipitation, whether it's how much rain there is, whether it is rain, whether it is snowfall, the indicator of ice or oil from the optical fluorescence sensor that we talked about before, the wind information, speed, direction, including the gust information, because often it is the gust that really affects ships coming in, the Beaufort scale categorization of that wind information, air temperature, air pressure, including the trend, so rising or falling, the visibility, the dew point, relative humidity, interesting indicators of the amount of moisture in the air, and then the wave height and direction, and the wave period. And then we've got the series of currents. So the surface current, level 2, level 3, and then the depth measurements at which level 2 and level 3 are taken. So the point of all that is, it's a comprehensive station measuring almost all the parameters that are relevant to ships coming in and out and making sure that they are navigating safely and efficiently. By giving port more information, not only does it help the ship captains make informed decisions, it allows the port to understand the risks involved and how many pilots they have available. They understand whether certain operations are safe, such as the movement of overhead cranes or loading on and off ships. And it gives them a better understanding of the typical environmental conditions, not just the storm conditions. So we'll delve into some of this data in the next section and look at some of the data that's being collected and maybe understand, to a deeper level what the conditions are, not just from an operational perspective, but from an environmental perspective. So now we're going to have a look at the web access for the online system. So we're going to go to a browser. We're going to visit the web address pentair.eagle.io, which is the portal from which you can access all your online information stored with Pentair. To give you a quick look around at the Pentair portal, this is our homepage. So when you log in, it gives you a quick summary about monitoring your data in real time. And that's the essential concept of Pentair.eagle.io, is that no matter where your data is, it's accessible through the browser as if you were running a control center or similar SCADA type system, real time, highly accessible, secure, be able to be accessed by multiple people at the same time and even collaborate on data. To give you an idea of some of the features provided on the online system, all you have to do is click on this features tab and it will give you the full list of everything that the system can do. If you scroll through, there's a whole heap of functionality in here to give you some of the kind of like highlights view. Your main view is the dashboard, and that is a completely customized view of whatever information you're measuring on site. It can be charts, maps, pictures. You can create whatever you want. You can scale it. You can put any kind of parameters next to each other. That's the primary view that most people should use when accessing a system, because that's something that you configure to give you the quickest, simplest understanding of what's happening on your site. If you've got a whole heap of sites, another view that's pretty powerful is the interactive map. It's based on a Google Map base layer on which all your sites are displayed, and you can have very quick summary information visible just by looking at the single map. So for instance, here you can see the parameters of each site. You can tell from the icon at each site whether there's an alarm or a problem occurring, and so that's another powerful view that you will use to see your system. Without constantly looking at the web page, another view or another feature that's quite powerful are the alarms and notifications. So this is the system's way of telling you that something important is going on and that you need to go and look at it yourself. From within alarms and notifications, you can configure the types of alarms that you see. You can choose whether you see maintenance, operation, or critical alarms, and whether you receive those alarms via your configured email address or via your configured SMS. And once a system is in alarm, you get to see the state of it quite quickly and in a simple summary type of view from which you can click through to see the details of that alarm. One of the final things, I guess, that's one of the key features is the access control. So when you put a system on Pentair.eagle.io, really you are in charge of it. So any data that you are collecting, how you view that data, who gets access to that data, what the alarms are, what the thresholds are, what the type of users of the system are, whether they're security administrators, whether they're operators. You control all the access and the sharing of that information. So, it's a framework for you to access your data and control how you view and distribute your information. So that's the quick overview. You can scroll all the way through this list of features. There's a lot in here: cameras, document storage, GPS tracking, historic information, quality control, and even giving you a roadmap for future functionality. But what we're going to do is we are going to go back up to the top and log into our system and show you the live operational system. So to log in, simply click the login button. It's already, because this is my account, it's already got my credentials stored in the system. And the one system that I'm going to show you that's relevant to what we've talked about before is a site that we've got in Canada called Duke Point, which is with one of our partners called Xanatos Marine and Nanaimo Port Authority. So by hovering over the site, you can see that straight away I'm getting a view of the site, and I'm seeing some of the information that is being measured at the site. Now this is a fully featured port monitoring station, so it's got almost everything that can be monitored. The map view, to give you an idea of where it is, it's in British Columbia, on Vancouver Island, just out of Vancouver itself. So as with any map navigation, you can keep clicking in on the map to get more and more detail. You can see we're directly to the west of Vancouver. It's a major port for shipping traffic travelling down the straits before they go out into the Pacific Ocean. It's at Nanaimo Port, which is the township of Nanaimo, sheltered from Gabriola Island at a place called Duke Point. So Duke Point is a loading terminal used by vessels coming in and out of port. So that's the map overview. If you have multiple stations, obviously you will see all your stations on the map. You will see the icons change color. There's a lot of dynamic information that you can get accessible through the map. As I highlighted before, the first view and the most powerful view is the dash view. So you can toggle through any of these to go have a look at the list of all your parameters, some charts, see the sequence of events. But generally the starting point for this is the dash view. The dash view is all created by you for you. So this station does have a predefined dashboard. If we want to add more information, it's simply a matter of clicking on the Add Tile button. And when information is configured, you can still reconfigure it by clicking the little pull-down option, which gives you the ability to rename, delete, duplicate, or change the properties of that tab. And if I wanted to change the way it was arranged or views, it's simply a matter of dragging that around and shifting it somewhere else. Now, for me, one of the most important parameters is this first parameter, which is the surface currents. It's coming from an AWAC, which is a acoustic Doppler current profiler, so it's a bottom-mounted AWAC, and we want to see the surface currents as one of the first views that we see. So you can see at the top of the dash, we've got surface currents, we've got wind speed and direction, we've got the wind gust, wind speed and direction, and we've got the tide cycle, so we can see exactly where we are in the tide cycle. So the very first part of the dash is what we've considered to be the most important part. If you want, you can scroll down through the dash and see all the other information that's being collected. So air temperature, pressure, relative humidity, dew point, rainfall, visibility, salinity, all the way through to various profiles of the current profile. And if we go all the way down to the bottom, we can see our wave height direction information. So I'll just go through a few of these. I'll show you what some of these parameters mean, and by looking at some real data, we will kind of see if we can get more sense out of the data by using some of the features included in the platform. I guess one of the interesting things. Obviously on first view we can see that some rain occurred on the 16th of August. It obviously wasn't much, but let's see what it actually was. So if you want to zoom in on anything, all you have to do is get these sliders for this chart. It will then help us zoom in. So I'll change the start and the end time, and I will look at the time period. Let's actually look at the day through which the rainfall occurred. So we can see that there's two bars of rainfall. Now what might be interesting is to see if that rain correlates to a drop in visibility. The forward scatter visibility sensor is able to reliably give us up to around 30 kilometre visibility information. Anything beyond that and it says we've got over 30 kilometres. So 30 kilometres is a very clear day. What we'll do is we'll have a look and see what the visibility did at the same time as this rainfall event. So let's take this visibility chart and we'll zoom into the same time period just out of interest and see what the visibility was doing through the period when the rainfall occurred. So we can see that at the time the rain that was occurring lines up with this low in visibility. Now if we zoom right in, let's see if we can get even more information, and we can see that from about 6 p.m. at night the rainfall actually occurred at 9 p.m. that night. So let's see how that lines up to the lowest visibility readings, and we can see that if we move this along this way, at around 9 p.m. at night, which is 9:30 around here, is exactly when the rainfall occurred. So during the peak of this rainfall event, it was a very small event, we're only getting around 0.8 of a millimetre, we can see that the visibility readings were getting down to around 6,000 metres, or 3,000 metres was the lowest value. And as we can see, that's right when the rainfall was occurring. So this demonstrates a lot of features of the chart. You can zoom in, you can have a look at detailed information, you can put a ruler on the system and see what the values are, and start to understand the relationship between various parameters. I guess that was one parameter that was interesting. When you've finished looking at that, you can just click the reset zoom buttons and it will take you back to the normal data set. Having a look through some other things that might be interesting. This is some interesting data. In this area we can see some water temperature information. Now if we have a look, it's clear that at the surface we are getting around 18 degree surface temperature measurements, while getting at the bottom down to around 10 degrees at the bottom. The problem there was I had to pick a point at which the two data points had the same timestamp. So the data on this is coming through, I believe, on every 10-minute basis. So if the measurements are at the same point, then when they're on the ruler you will see both of them showed at the same time. So we can see that from the surface to the floor there was a gradient of 8.3 degrees difference between the temperature measurements. Obviously that's a huge gradient. There are periods at which the surface gets cold through some mixing. I think we'll find these related to the rainfall event that we're looking at before, and you can see that there's also periods when a warmer bottom current starts to mix, and we start to get some warmer ocean floor measurements. But we can see that there's a large gradient between the surface and the bottom temperatures. Now, to try and understand that, let's have a look at some current information. And really, like I said before, this is the primary function of this station, is to help ships come in and out of port. So anything that's going to affect their navigation is a primary parameter. So we want to obviously look at tide, we want to look at wind speed, we want to look at barometric pressure, which is a leading indicator of storm activity. But one of the main parameters are the currents. So shallow vessels, obviously mainly concerned about what's happening at the surface. And this image here shows us over the last 24-hour period, so the 18th of August through to the 19th of August, what the surface currents were at a depth of 1 metre. And we can see that really a lot of it is in this blue zone, which is less than 0.2 knots, with occasional currents in the 0.2 to 0.4 knots. So surface currents, this 24-hour period has been very low surface currents. Now, if we scroll all the way down to the bottom, we can see not only surface currents, but also currents at depth. And if we go all the way down, we can have a look and see that at 19 metres, at 18 metres, at 13 metres, we can see there's actually quite a strong bottom current. So where we were seeing that surface temperature, bottom temperature information, that told us there was some strong layering occurring. And down at 18, 19 metres, we can see that in general, the currents are strongly coming from the easterly direction. And a lot of the time, we are getting some very strong currents. So at 12% of the time, we are getting an easterly current of 1 to 1.2 knots. So it's telling us a lot of information that, obviously it depends on how close to the surface that becomes, but that helps explain why we are getting this layering between bottom and surface temperatures. So there's a lot of detail on the dash. That's your primary view, gives you access to all the information that you're measuring on site. How you, what dashboards and tiles are actually used is up to you. You can click the add tile if you want to add more information. But yeah, that's the basic view of the Pentair Eagle IO. As you can see, real-time information, updated dynamically, it's interactive, it's secure, HTTPS, so no one else can get access. You manage your system, so if I want to change any of my profile or settings or manage alarms, you can do it all through this web page. Yeah, that's a quick overview. Thanks for watching. I'll come back with more details.